Hello, so I've got the next problem set for you, and it's really not a problem set. It's more like a research assignment. So let's take a look. All right, we're going to estimate an airline industry marginal cost function. So I've found some data um, from Caves, Christensen, and Trethewey that was published in Economic Inquiry. It's some airline industry cost data. We'll look at it in a second. But imagine it's 1984, 6 years after airline deregulation. You're an economist working for a trunk airline. Your firm is considering merging with a local airline, local in the sense that it's a smaller airline. You've been asked to estimate the marginal cost function after the merger. And once you have the marginal cost function, we want to figure out what the profit maximizing output will be after the merger at prices of $2,000 and $2,500 per unit. So obviously you don't know where to begin, but you do find that an airline industry analyst has conducted a similar study for all airlines for the years 1981 and 1982. So here's the result from that study. This is the airline industry total cost function, and these years aren't correct. That's 1981 and 82. I labeled that the wrong way. Here's the data points and the trend line that was fit to that. The best line is a quadratic. So here you see the squared term. Y in this case is total cost, and X is output, and the R squared is 0.85. So given this total cost function, the marginal cost function is equal to 114 plus 972 times Q. And that's just the first derivative of this cost function. At prices of 2,000 and 2,500, output is equal to 1.94 at 2,000 and 2.45 at 2,500. Okay, and to find that, I set price 2,000 equal to marginal cost, these numbers right here, and solve for Q. So just a little bit of algebra. So the assignment is to write a 250 plus word paragraph describing your methods and results. So the paragraph would describe the regression analysis that you tried, your test for best functional form, whether it's linear, quadratic, or cubic. And I'd like to see the Microsoft Excel regression output for your best model only. So the statistical results, not just the graphical analysis, although you could include that if you'd like. A few things to remember. The data, data are messy. Data aren't always as clean as you'll find in a textbook. As you're looking for best statistical fit, just remember that your ability to estimate a cost curve and an upward sloping marginal cost curve depends on the quality of the data. Your best statistical fit might be a linear total cost curve, which will give you a linear, a flat marginal cost curve. In that case, there's no unique answer for the output levels, and you just need to report that and tell me that at a price of 2,000, that's going to be $500 greater than the marginal cost, which is going to be equal to the average cost, average variable cost for that airline. Okay, so here's the data assignments. We'll look at the data in just a second. So hopefully you can find your name here in alphabetical order. Your trunk airline, you're working for American, Braniff, Continental, Delta, Eastern, National, Northwest, Pan Am, TWA, or United, or Western. And then these things start over again. So we've got, I think, 11 trunk airlines. So there's 2 workers for each airline. And then there's 4 local airlines: Air West, Allegheny, Frontier, and Piedmont. And so the analysis is to see what output would be, see what that marginal cost curve would be the total cost curve would be if Continental merges with Air West, or more accurately, buys up Air West. Okay, so let's go back to As You Learn here. If you're interested in the source of the data, Caves, Christensen, and Trethewey, let's see, there's the title, abstract, and there's the trunk and local airlines. If you're interested in the context of this study, you can skim through this paper. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 trunk airlines here. Might be one more in the data. I'm not sure. It doesn't matter. And then the locals, there's 1, 2, 3, 4, 5, 6, and we don't have Ozark or Texas International. The time series on those aren't long enough, and so they go on and do a bunch of stuff with these data that we're not going to do. All right, the airline industry data. If you download the spreadsheet, and here it comes, I think. Okay, here it is. All right. So the data set includes the year of the data, the airline, the firm, whether it's trunk. If it's 0, then that's a local airline. Whether this was after deregulation. We have a dummy variable. Airline deregulation occurred in 1978, and this is equal to 1 every year after 1978. The time variable includes the year of the study. The data goes from 1970 to 1984. Output is an index number, and I have added 1 to the index number, so if you decide to square or cube output, then the number will go up and not down. Cost, this is in millions of dollars. Then there's 3 airline industry variables: load factor, stage length, and points. I think load factor goes from 0 to 1, and that's the percentage of airline seats that are occupied on average for the airline. Stage length is the average number of miles per flight, and points is the number of cities that the airline travels to. So you see, let's go from a local, so Piedmont Airlines, which were merged with Allegheny and became U.S. Airways, and compare that to American. So the output for American is greater, a trunk airline is greater than for a local airline. Costs are higher for the trunk. Capacity is about the same for this comparison. The length of flights is about twice as great for the trunk as for the local, and number of nodes for these two is about the same. I don't know if overall, yeah, there's a lot of nodes for American later years. I'm not sure if that result holds up for the entire data, but those variables can be important for cost estimation, but we're not going to do that in this situation. There's the spreadsheet for the data assignments again. Here's a quick explanation of the data set where they borrowed it from Caves, Trethewey, and Wendell, or at least 2 of the authors. There's a summary of the data set in the years. This is a screenshot from a book. And an example. Okay, so here is the picture that I put on the Word document. And there I've got the linear cost curve for the correct number of years. Yeah, I think the picture that I have in the assignment might be for all the years of the data, but it doesn't matter. So we're going to take a look and see how this works. So let's say you've got 1981 and 1982 as the years you're looking at for all of the airlines in the study. We've got trunk and local airlines. So I purposely put output in a column right in front of cost. Okay, if you highlight those and click on Insert, then click on the scatter plot for charts and the one with just dots, you get a picture of the data, and on the vertical axis is cost and on the horizontal axis is output. Okay, if you right mouse click on the dots, then you can add a trend line. And let's see if I can, there we go. Okay, so the three functional forms that we considered in class, and my stupid face is in the way. I want to, there we go. There we go, that we looked at in class. Trend line, okay, or linear. And I was clicking on the power function, but that's not what we want to do. We will look at second and third order polynomials, and those are the quadratic and cubic functions. If you look at the power and display the r squared on the chart, that's pretty high, that's nice. Display the equation on the chart, then this function raises, gives you total cost equals a number times output raised to a power. So that's a power function. We don't want to do that. Okay, so look at linear. And again, I've checked display equation on chart and display r squared value on chart. So polynomial of order 2 is a quadratic function. So here's the intercept, minus 3423 plus the linear term plus 3794 times x, and then minus the squared term, minus 354.63 x squared. So the linear, so it rearranges the A, B's, and C's like we talked about in class, or the D's, E's, and F's, or whatever we call them. But it's still the same function. Polynomial of order 2 increases our r squared, but the shape of the total cost curve is not consistent with our theory. So here it goes from being slightly convex to concave. It's shaped like a total product curve, where the total cost curve should be shaped like the inverse of the total product curve. And our signs are opposite of what you'd expect. You'd want the linear term to have a positive sign, the squared term to have a negative sign, and the cube term to have a positive sign. And it turns out when I create the squared and the cubed variables in Excel and estimate the model, these coefficient estimates are not statistically significant. Actually, none of the three are. They're jointly significant, which basically tells us that the model is roughly linear, which there's not much curvature to that. So if I was going to go with, look at these data, I would try the quadratic function and the linear function and see what the coefficients look like. So let's see. So let's do that. So to estimate the regression model, I'm going to insert a column and call this output 2 and square output. So G2 times G2 gives me a squared term. And let's go data analysis, regression. What do I have in there? So let's get rid of that. So cost is I1 to I23, and then our X range is G and H. I've got labels. Just click OK. And so here is the summary output. Let's see what we got. We have a negative intercept, and for most of these data, because that output level is an index number that reflects output but doesn't really measure the number of flights that are taking place, your vertical intercept on your cost equations are going to be negative, and so that's part of the data are messy piece. So kind of ignore that. The linear term here, output, is 3794, and its standard error is much smaller than the coefficient, and so our t statistic is 5.3. The squared term is negative, like you'd expect with a cost equation. Actually, that's not correct. The squared term is negative, which to have a valid cost equation, that term needs to be positive, so the marginal cost equation is going to slope upwards. This t statistic is statistically significant at the 94% confidence level, but in terms of decision making, that model doesn't conform to theory. We're going to have a downward sloping marginal cost equation, and so we're going to reject that model for a linear model. So let's go back to the data. Student note, an example. Okay, so data analysis, regression, and I'm going to get rid of my squared term. So here's a linear cost equation. The R squared is about the same. So we're still explaining as much of the cost as we did with the quadratic term included. So R squared here is 0.974. With the quadratic, it's 0.978. So not much difference there. So we're not losing much by not including that variable. And our output, coefficient on output is 2404, which means that the marginal cost is $2,004. Okay, so if the price is $2,000, price is less than marginal cost, so we don't want to produce in that situation. And if price is $2,500, then that is above the marginal cost, and there's some positive output level that we want to pursue. So to include this into your one paragraph output, right click or highlight the output, right click, let's see, copy, and then I want you to paste the image into your Word document. So paste special, and the icon was there. That would work. Let's go paste special, and it keeps going away, but my stupid face wasn't in the way. All right, I'm trying to get Excel to, okay. Actually, we can just go down here. So paste special, and the clipboard with the picture there is pasting an image. You can do this in Word too, but I like to do it in Excel once, and then copy the image, and you can paste that right into your Word document. So that's the assignment. If you have any questions, let me know.